Good morning, everyone. It's very good morning. Shall we begin the session? Yes, today's topic is instruction encoding. That is how to use the instruction encoding. But what are the various methods that is used for the instruction encoding? Yes, in the last class we have discussed some of the holds condition, stop condition that is available. And this is known as the instruction encoding. That is a byte level encoding of the instructions, and each instruction requires between 1 and 6 bytes that are also encrypted, that are also used with the function that can range from 0 to the 0 into x or 0xb. So this instruction encoding will be used for the high code level, for the low order level, or the function part that is used with the RRMOV1, that is associated with the register identifier, that is ID, ranging from the 0 to 7, and the numbering of the registers in Y86 also matches what is used is known as the IA32, and the program registers also used with this, that is known as this. So this will ranging from the 0 to 7, and the numbering of the registers in Y86 matches with what is known as the IA32. And the program registers are also stored within the CPU in a register file, small random memory, where the register's ID serves as a Y86 instruction. So there are multiple registers: name, number 0, number 2, number 1, number 3, number 4, number 5, 6, 7, and F. That is EAX, ECX, EDX, EBX, ESP, EBP, ESI, EDI, and then F no registers. This is Y86 program register identifier, and each of the 8 program registers has an associated identifier ranging from the 0 to 7, and this is the register field of an instruction that indicates the absence of a register operand, that is used with the ID value 0xf, that is used in the instruction encoding and within our hardware design when we need to indicate that no register could be accessed or should be accessed. That is used with the additional register specifier byte that specifies either 2 or one of the 2 digits registers, that is range from the RA and the RB that is given in the figure 4.2 that is available over there. This is figure 4.2. This is IA and the IA2. So we use the registers branching calling that do not have a register specifier byte, those that require just one register operand, that is IR move, push 1, perf 1, that have other register specifier that's set to the value 0f, and this convention will prove useful in our processor implementation. And this instruction also requires an additional 4 byte constant words, and this word can serve as an intermediate or immediate data for IR move 1, displacement for RM move 1, and the MR move 1 address specifier, and also use the destination of the branches and the calls that is used with the call destination that is used as absolute addresses rather than using the PC relative references seen in the IA32. And whatever the processor that uses the PC relative addressing to give more compact encoding of the branch instruction, and also allows the code to be copied from one memory to the another without the need to update all of the branch target addresses. Since we are concerned with the simplicity, we have to use the absolute referencing addressing with the little encoding with the example that is used to generate the byte encoding of the instruction RMO1 ESP EDX in the hexadecimal format. Now this is the byte with the Y86 that is listed with the sequence that encodes, that is used with the invalid byte in the sequence that shows how the instruction sequence goes up, up, up with the RISC and the CISC instruction set. Now this RISC Y86 exception includes a status code that is used with the stat describing the overall state of the executing program, that is used for the programming code that is used for the value 1, value 2 named AOK that indicate that the program is executing automatically normally, with the other code that indicates some types of the exception, also exception handling that occupies some codes with the halt instruction, and code 3 names ADR that also uses with the ADR that indicates the processor, whatever the processor whatever the processor says, that indicates that the processor attempted to read out or form or write an empty code invalid memory address either while fetching an instruction or while reading or writing the data. Then we limit the maximum address, that is the exact limit by the implementation, and can access to the address beyond this limit on the trigger on an ADR exception. And code 4 name INS indicate that an invalid instruction code has been encountered. That is used with a normal execution, that is used with a normal operation. HLT hold instruction encountered, ADR invalid address encountered, INS invalid instruction encountered. That is used with the processor that encountered that any of the exception listed above this one. And in a more complete design, the processor would typically invoke an exception handler procedure that is designed to handle the specific types of the exception encountered, that is also known as a user-defined signal handler. Then y86 programs that is used with the IA32 and the y86 assembly code for the following C functions. This is int sum, int asterisk start, int count, sum equals to 0. Now this is used with the sum equals to 0, then while count. So we are using the while count, then there is a curly braces, sum plus equals to into start. That means it is adding up with the multiplication of the start value only, then start plus count minus minus, and at last there is a return sum. Then IA code 32 code was generated by the GCC compiler, and this is essentially the same, that is except that y86 sometimes required two instructions to accomplish what can be done with a single IA32 instruction that is used. We have seen for IA32 that includes the use of the stack and the frame pointer, and for simplicity it does not allow or follows the IA32 convention of having some register that is designated as a callers or the callee save registers. This is IA32, Y86, sum, push, end sum, comparison of the Y86 with the I32 instructions. This computes the sum of an integer array, and this is also different from the IA32, mainly in that it may require the multiple instruction to perform what can be done with a single IA32 instruction. So in this program, words beginning with dot are assembler directives telling the assembler to adjust the address at which it is generating the code or to insert some words of the data. And the directive dot post 0 indicates that the assembler should begin generating the code starting at the address 0. This is the starting address for all y86 programs. And the next two instructions initializes the stack and the frame pointer that is seen by the label stack that is declared at the end of the program to indicate the 0 into 100 using the positive directive. And our stack will therefore start at this address and grow towards the lower addresses, and we will must ensure that the stack does not grow so large it overwrites the code or the other program data. And lines 9 to 13 of the program also declares an array of the 4 words having the value 0xt, 0xc, 0xb, 0xa. There are 000, that is a label value that also denotes the start of the array and is a line and 4-bit or 4-byte boundary with a line directive, and this shows the main procedure that calls the function sum on the 4-word array and then holds. Then holds means then stop out for some moment. This is the sum function. This is the looping that is available. This is the end function. As per this example that shows, since only tool for creating y86 is an assembler, the programmer must perform the task that is ordinarily delegated to the compiler, linker, and the runtime system. And fortunately, we only do this for the small programs for which simple mechanisms also suffix that is also used, that is implementing and instruction set simulator that will use YIS. That purpose is to model the instructions of the y86 instruction that is used for the debugging, because the actual hardware is used for the debugging part that will be used for this array. Now this execution begins at the address 0. This is the positive 0. Then array of the 4 element, that is the align 4. Then the main, that is a push L, IR or RR move L, int sum, int start, int count, ECX, EBA. Then some y86 instruction detail that performs a program state in a straightforward manner, and so defining the intended effect of each instruction is not difficult, and the two unusual instruction combination however also requires special attention, that is used with the push shell, that is used with the push p, that is stack pointer by the 4, and also write the registers value to the memory. And for the y86 processor, let's us adopt the same convention that is used with the IA32. This is the text global protest, push test, push, move, push shell, propel, subel, leave, RAT. That is used with the ESP to the value read from the memory or to the incremented stack pointer. Now this is the combination circuit and the Boolean expression, that is the main part. So just read out this thing, whatever we have done. In the next 5 minutes, we will start with the next one circuit. Any doubts, anyone till here? Okay. Next is the Boolean expression or the Boolean algebra that is made with the circuits. That may be a AND gate, that may be a OR gate, XOR gate. So there are multiple logic gates that are known as the combination circuit that is used with the combination blocks, and the output of 2 or more logic gates cannot be connected together, otherwise the two could try to derive the right in the opposite direction, possibly carrying or causing an invalid voltage or a circuit malfunction. And the network must be acyclic, that is, there cannot be a path through a series of gates that forms a loop in the network, and such loops can cause ambiguity in the function computed by the network. Whatever the network we are choosing, so there is an ambiguity in the network, there is a malfunctioning in the network that is computed by this network. And this figure that shows an simple combination circuit that will find useful, that requires or that will take the two inputs, one is A, one is B. Two inputs are given, then bit equal, one is a AND gate, this is a NOT gate, this is a equal gate or equality gate. This shows an example of the simple combination circuit that will be found useful or the find useful, that our two inputs A and B then generates a single output EQ or the equation such that the output will equal 1 if either A and B are both 1, that is deducted by the upper end or both the 0. Now we will write this network in the SCL as Boolean equals to A and B and not A and not B. And this code simply defines the bit level that is denoted by the equality sign as a function of the inputs A and B. And as per this example shows, SCL uses the C style syntax with the equals to associating a single name or the signal name that is used with an expression. Unlike C, however, we do not view this as in performing computation and assigning the result to some memory location. Instead, it is simply a way to give a name to this expression, a name to this profile. Now this figure that also shows another example of the simple but useful combination circuit known as a multiplexer, that is known as a MUX, and this also select a value from among the different data signals depending on the value of a control logic signal, control multiplexer. There are two data signals that are used or input bits, that is A and B, while the control signal is an input bit, that is a S. So S is also used, P is also used for the data signal, that is circuit is 0. And in this circuit we can see that the two AND gates determine whether to pass their respective data input to the OR gate, or either use the AND gate that passes a signal B when S is 0. This is bool out equals to S and A, or not S and B. Now, when we use the high control language or the high control language, that expression demonstrates a clear parallel between the computational data, between the combination logic circuit and the logic expression in the C. They both use a Boolean operations to compute the function, to compute the data that is used with the input, and several differences between these two arrays of expressing computations that are worth noting. And since a combination circuit consists of the series of the logic gate, it has a property that the output continually responds to the changes in the input. And if some input to the circuit changes, This will use with the input to the circuit changes, then after some delay the output will change accordingly, and in contrast a C expression is also evaluated when it is encountered during the execution of a program. This is the word level combination circuit and the SCL integer expressions. This is the bit equal combination circuit to perform the word level computation that are constructed using the logic gates to compute the individual bits of the output word. Then bool equals to A equals to B. So now comparison is taken out between the A and B. A equals to B, where equals denote assignment, double equals denote the equality operator. This is the word level multiplexer circuit. The output will give the input when the signal S is 1. So we are giving the S signal 1 and it will equal B otherwise, and the multiplexers are described in the SCL using the case expression. So this is select 1 expression 1, select 2 expression 2, select K expression K. And this combines with a series of the cases where case consists of a Boolean expression select that indicates when this case could be selected, integer expression indicates the resulting value. Then int out equals to SA1B, that is a SCL or used with the SCL. Then there are two signals S1 and the S0 and the 2-bit binary number that is also expressed in the SCL to describe the different combinations of the control bit pattern. Then this is a multiplexer 4. This is the output, and observe that the selection expression can sometimes be simplified with the first matching case that is selected, and there are also other signals that is used with the final example. Suppose we want to design a logic circuit that finds a minimum value among a set of the words A and B or ABC, that is diagram with this one. This is the min3 that is used with the ALU, arithmetic, and the logical circuit. Then set membership is also the same, that is we are using the set membership code for the how to use and what are the various clocking registers that is used in the expression IXPR, candidate matches, IXPR or IEXPR, that is I experiment 1, I through I experiment 2 are all integers expression. This is one of the case. That means we have to check between these I expression 1, 2 till K. Then bool S1 equals to code in 2, 3. Bool S0 equals to code in 1, 3. Now, next is a memory and the clocking. This memory and clocking I'm going to take within the next class, that is the tomorrow's class. Because what is a memory? As we know, memory is where we store the data, where we collect the data, and there are multiple types of the memory like registers, primary memory, secondary memory. Clock means how the time lapses or how we use the time in the computer, that is the clock cycle or the clock. So we will discuss this in the next class, that is in the tomorrow's class. And till now, any doubts, anyone? So please ask the doubts from me, because yes. So please ask the doubts if there is any doubt regarding this, regarding assignment, anything that you want to ask. All right. So we'll be tomorrow with a new topic, that is a memory and the clock. All right. Bye bye everyone. One more thing I want to share with you, that please submit the assignments on the time, because you have to submit the assignment on the time so that you get the certificate. Certificate is very important. You get the certificate whenever you want. So please submit the assignment all the time. It's my reminder to all of you that please submit the assignment.